So I want to go over some examples of rational functions. Rational means fraction. And so with rational, many of the rational functions we'll be working with are going to be hyperbolas. The graph will be a hyperbola which has asymptotes. You may remember those from pre-calculus. And to get the asymptote, it's going to be helpful to do division, long division or synthetic division. So if we divide x minus 3 into 2x squared minus 7x plus 9, divide the highest power of x by the highest power of x. 2x squared divided by x is 2x, so we put the 2x on top. Multiply 2x times each term, you get 2x squared minus 6x. And then we want to subtract, but the way you subtract with algebraic expressions, you want to change the signs, add or subtract like terms according to the sign. So change the signs here, draw the line, change the signs. 2 minus 2 is 0, negative 7 plus 6 is negative 1x. And then bring down the 9. And then divide again. Negative 1x divided by x is negative 1. Multiply, get negative 1x plus 3. Draw the line, change the signs. You have here remainder 6. 6 over x minus 3. So this tells us our asymptotes. That we'll have a slanted asymptote with slope 2, y equal 2x minus 1. This is our slanted asymptote. And then we have a vertical asymptote, x equals 3. Okay, the vertical asymptote occurs when the denominator is 0. So if x is 3, we'll have denominator 0 there. And that gives us a vertical asymptote. Slanted asymptote is also called an oblique asymptote. Okay? So we have a slanted or oblique, y equal 2x minus 1. Vertical asymptote, x equals 3. Hyperbolas have two asymptotes. The hyperbolas that are functions will have a vertical asymptote and one other asymptote. And then we can make a table of values and sketch the graph. So we could use either formula for we could either use the original formula or we could use this form here, whichever is more convenient. Let's see. Okay, so we want to pick some values for x and compute f of x. And I want to pick at least 2 points on either side of the asymptote. The asymptote is at x equals 3. And I want to pick some points on either side of that. So if we put in 0, you get 9 divided by negative 3, which is negative 3. If x is 2, 2 squared is 4, 4 times 2 is 8, so we'll have 8. 2 times 7 is 14, 8 minus 14 plus 9, over 2 minus 3 is negative 1. So this is it comes out to be negative 3 also. Get minus 6 plus 9 is 3, yeah, negative 3. If x is 4, 4 squared is 16, 16 times 2 is 32, 4 times 7 is 28, plus 9 over 4 minus 3 is 1, so this is going to be 13. If x is 5, 5 times 5 is 25, times 2 is 50. 5 times 7 is 35, plus 9 over 5 minus 3 is 2. So this all comes out to be 12. Okay. Okay. So then we want to draw a coordinate system and plot the points. Okay, so let's say 1, 2, 3, 4, 5. And we want to go at least up to, let's say 5, 10, 15. Okay, so I scaled the x and the y differently because our y values are bigger than the x values, so I didn't want to. Sometimes it's not convenient to. It's more convenient to scale them differently sometimes. Okay, so we have an vertical asymptote at x equals 3, so I'll put that in here with a dotted line. And then we have a slanted asymptote, y equal 2x minus 1, and so the y-intercept there is negative 1, and if you go over, the slope is 2, so if you go over 1, you go up 2. Let's go over 3. If you go over 3, you go up 6, so that's about right here. And put that in with a slanted line. A dotted line also. So those are the asymptotes, and then we can plot the points. So we have 0 left or right down 3, and 2 to the right down 3. And we want to connect these dots and extend it toward the asymptotes. Hyperbolas never cross. Some functions will maybe cross an asymptote, but hyperbolas never cross. They get closer and closer to the asymptote, but they don't cross. 4 to the right up 13, about right here, and 5 to the right up 12, and again connect the dots, extend it toward the asymptotes. Next week we're going to be talking about limits, and this is kind of a visual illustration of limits, or the asymptotes are. For the vertical asymptote, as x approaches 3 from the left, the function values get closer and closer to minus infinity. They go out to minus infinity. As x approaches 3 from the right, the function values approach positive infinity. But we'll get into limits a little bit later, but this gives a nice visual representation of limits. And the next example, it will even a better illustration of limits. Okay, here we have another rational function, and again, we're going to have some asymptotes, and to get the asymptotes, we can divide x plus 3 into 2x minus 1. Divide the highest power of x by the highest power of x. So 2x divided by x is 2. And then multiply 2x plus 6. Draw the line, change the signs, add or subtract like terms according to the sign. We're going to get remainder minus 7. I'm getting sloppy with my writing here. Okay, so we have a vertical asymptote, x equal negative 3. That's the vertical. And then the horizontal, this has slope 0, so it's horizontal, it's not slanted. Horizontal asymptote y equal 2. So those are our two asymptotes. And then we can plot some points and sketch the graph. Okay. Okay, so we want to pick points on either side of the asymptote. So I'll say negative 5, negative 4, negative 3. That's undefined. That's our asymptote. Okay, I'm frozen here. Let's unfreeze. Okay, looks like I'm unfrozen. Okay. Let's say negative 2 and 0. Okay, so I have 2 points on either side of the vertical asymptote, and then I can compute f of x. So 2 times negative 5 is negative 10, minus 1, negative 5 plus 3 is negative 2. So this is going to be negative 11 over negative 2. It's going to be about 5 1/2. If x is negative 4, we're going to have negative 8 minus 1 over negative 1. That's going to be negative 9 over negative 1, which would be 9. If x is negative 2, we're going to have negative 4 minus 1 over 1, negative 5. If x is 0, we're going to have negative 1/3. Okay, so then we can plot the points. Okay, so we have 1, 2, 3, 4, 5, 5. And let's see, let's say 5, 10. Okay, so so then we can plot the points. So we have 5 to the left. Oh, let's do the asymptotes first. So we have a vertical asymptote at x equal negative 3. Make a dotted line there. And then we have a horizontal asymptote of y equal 2. So we'll have a dotted line there also. And then we can plot the points. So we have 5 to the left, down 5 1/2. No, up 5 1/2 rather. 5 to the left, up 5 1/2. Something like right here. 4 to the left, up 9. And then we can connect the dots, extend it toward the asymptotes. And then we have 2 to the left, down 5. Right here. 0 left or right, down 1/3. And connect the dots, extend it toward the asymptotes. So that's our hyperbola. And again, this is nicely illustrates limits. And we'll talk more about limits next week, but we see that the limit as x goes to negative 3 from the left is going to be positive infinity. As x approaches negative 3 from the right, that goes to negative infinity. As x goes to infinity, f of x goes to 2, gets closer and closer to the line y equal 2. As x goes to minus infinity, f of x also approaches positive 2. So anyway, we'll talk about more about limits next week. But these hyperbolas really nicely illustrate the idea of limits. Okay, so the first two examples were hyperbolas, but here's another rational function that's not a hyperbola. This is actually going to have two vertical asymptotes. Again, we can. I like to do the division to get the asymptotes. So we want to divide x minus 4 into x squared. If you want, we could put a placeholder here, or there's no. We have no constant term in the numerator, so we could put 0 for a placeholder. We want to divide the highest power of x by the highest power of x. So x squared divided by x squared is 1. Any number divided by itself is 1. And then you multiply 1 times each term of the divisor. Draw the line, change the signs. And we have 0 plus 4 is 4, so you have remainder 4. So it would be 4 over x squared minus 4. So the denominator will be 0 when x is either 2 or minus 2. So we're going to have two vertical asymptotes. X equal either positive 2 or negative 2 will be our vertical asymptotes. And we'll also have a horizontal asymptote, y equal 1. Okay. So those are our 3 asymptotes here. So this is not a hyperbola. Hyperbolas only have 2 asymptotes, but this one has 3. We have a horizontal asymptote, y equal 1, and 2 vertical asymptotes, x equal 2 or negative 2. And then we can make a table of values and plot the points. One thing to notice here is this is an even function. So if we put in 2 here, you're going to get the same result as you put in negative 2. If you put in 1, you get the same result as negative 1. So this is an even function. Okay, so let's pick some values for x. So we'll say minus 4, minus 3, minus 2 is going to be undefined. Minus 1, 0, 1, 2 is undefined, and 3 and 4. So if we put in either 4 or negative 4, we're going to get 16 over 16 minus 4 is 12. So this reduces, this is 1 and 1/3. And it's going to be the same for positive 4. It's going to be 1 and 1/3. Negative 3, going to have 9. 9 minus 4 is 5. 9/5, which is 1 and 4/5. And that'll be the same with positive 3, which is 1 and 4/5. Negative 1, you're going to have 1 over negative 3, or negative 1/3. That's the same with positive 1. And 0 is going to be 0. Okay. So we have the 2 asymptotes that kind of split the graph into 3 pieces. Okay, so then we can draw a coordinate system and plot the point. Yeah, I think I'll make these y numbers more spread out. I'm scaling the y and the x differently because our y values are pretty small and our x values are bigger. Okay, so we have the vertical asymptotes at 2 and negative 2. And horizontal asymptote at 1. And then we can plot the points. So we have 4 to the left, up 1 and 1/3. It's about right here. 3 to the left, up 1 and 4/5. And connect the dots and toward the asymptotes. 1 to the left, down 1/3. 0, 0. 1 to the right, down 1/3. Connect the dots, then toward the asymptotes. And then we have 2 to the right, 3 to the right, up 1 and 4/5. And 4 to the right, up 1 and 1/3. Connect the dots, then toward the asymptotes. Okay, so that's not a hyperbola. As far as I know, there's no generally agreed upon name for this particular shape, but it's not a hyperbola. And again, this sort of illustrates limits. As x goes to infinity or negative infinity, the graph gets closer and closer to 1. As x approaches negative 2 from the left, the f of x goes to infinity. As x approaches negative 2 from the right, it goes to negative infinity. and as x approaches positive 2 from the left, it goes to negative infinity. As x approaches positive 2 from the right, f of x goes to positive infinity. So so again, this these rational functions nicely illustrate the concept of limits, which we will get into in more detail next week. F of x equal 1 over x squared plus 1. Another example here. This one we almost don't need to divide, but I'll divide anyway. We can put 0 for a placeholder. With this, the numerator does not have an x squared term, so we can put 0 for a placeholder. And divide the highest power of x divided by the highest power of x. If we want, we can put a 1 here, 1x squared. 0x squared divided by 1x squared is 0. And then multiply 0 plus 0, 0x squared plus 0. Draw the line, change the signs, add or subtract like terms according to the sign. We get remainder of 1. Okay, so we're going to have horizontal asymptote y equals 0. Is going to be our horizontal asymptote. And there's no vertical asymptote because the denominator, as long as we're working with the real number system, x squared plus 1 cannot be 0. So it's no vertical asymptote. Okay, so we have horizontal asymptote y equals 0, no vertical asymptote. So again, this is another rational function that's not a hyperbola. So many of the rational functions are going to be hyperbolas, but there's also not all of them are going to be hyperbolas. Okay, so we can make a table of values and plot the graph. We have 1 over x squared plus 1. Let's say negative 2, negative 1, 0, 1. This is another even function, actually. If we put in negative 2 here, we have 1 over 4 plus 1, or 1/5. And positive 2 will be the same thing. It's going to be 1/5. If we put in negative 1, we have 1 over 1 plus 1, or 1/2. Same with positive 1. It's going to be 1/2. Put in 0, 1 over 0 plus 1. It's going to be 1. And then we can plot the points and get the graph. Okay. So 2 to the left up 1/5, 1 to the left up 1/2, 0 left to right up 1, 1 to the right up 1/2, 2 to the right up 1/5, connect the dots, and then extend it toward the asymptote. So the this is a bell-shaped graph. It's one of the bell curves of statistics. It's actually a T distribution with 1 degree of freedom. Well, 2 degrees of, is it 1? No, 2. I think 2 degrees of freedom, I think. Okay. One of the bell curves of statistics. But and this illustrates limits again. As x goes to infinity, f of x gets closer and closer to 0. Also, f x goes to minus infinity. It gets closer and closer to 0. Okay, another example of a rational function. Again, we want to divide to check for asymptotes. divide the highest power of x by the highest power of x. X squared divided by x is x. So x goes on top, and multiply. You get x squared plus 2x. Draw the line, change the signs, add or subtract like terms according to the sign. You get remainder of negative 1x. Divide again. Negative 1x divided by x is negative 1. Multiply, and you get negative 1x minus 2. Draw the line, change the signs. You get remainder 0. Okay. Okay, so this is if x is negative 2, it looks like we might have an asymptote, vertical asymptote of x equal negative 2, but at negative 2 we get 0 over 0, so there's no asymptote, no vertical asymptote here. And actually there's no horizontal asymptote either. This is actually just a straight line with a hole in it. If x is negative 2, if x equals negative 2, 0 over 0 is indeterminate. It's an indeterminate form that we'll work with a little bit later in the semester, but 0 over 0 is called an indeterminate form. So this graph is just going to be undefined there, but there's no asymptote, and so we'll make a table of values. And we don't need a lot of values here. What I'm going to just do x minus 1 for x not equal to negative 2. Okay, so I'm going to put negative 2 in here anyway. The function is undefined when x is negative 2, but we need to know where the hole is. This is going to be the hole, and it's going to be negative 2 minus 1 is negative 3. There's going to be a hole at that point. And really, we only need one other point. Let's do the y-intercept. 0 minus 1 is negative 1, and then we can draw a coordinate system and sketch the graph. Yeah, I need to go a little bit further. I'm going to label this. Okay. Okay. So there's a hole at negative 2, negative 3. So it's 2 to the left, down 3. That's where our hole is. And then we have a point at 0, negative 1, and we want to connect the dots, and that's our function. We have it's just a straight line with a hole in it. Okay, so again, oftentimes the rational functions are going to be hyperbolas, but not all the time. This is just a straight line with a hole. Okay, so I think yeah, this function here also is illustrated limits. Also, we can talk about the limit as x approaches negative 3. So f of negative 3, even though f of negative 3 is undefined, f of negative 2 rather, f of negative 2 is undefined, it still has a limit there. So and we'll talk again more about this next week, but we can say that the limit of f of x as x approaches negative 2 is equal to negative 3. Even though the function is not defined there, the limit itself is defined. As the closer we get, x gets to negative 2, the closer f of x gets to negative 3. And that concludes this presentation.